Hey, okay, so let's get on to today's stuff. But while we're talking, I don't know what made me think of this. I want to just try this. I haven't done this in a class in a long time. How many of you have a birthday in January? January birthdays? Okay. What day? 6th? Okay. Any other Januaries? February? Just one? Never mind. March? March? Just one? April? Okay. What day? Okay. May? What day? 26th? What are we at? May? June? Just one June? Sorry. July? Just, okay, so what day? 2nd? There. August? '31st. Okay. September? Go ahead. Oof. Okay. Where are we at? October? Wait. September? That was September, right? October? 31st? Okay. November? December? What do you got? 16th? 3rd. Okay. So no one had the same birthday. Do you think it was good odds or bad odds that we would have a birthday? Bad odds? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 21. In a room full of 23 people, it's about a coin flip. It's about a coin flip. It doesn't seem like that, right? But beginning of the semester, if you walk into a class, it's like 30 people in there, it's better odds than a coin flip that you're going to have 2 people share the same birthday. That doesn't seem right, does it? How would you prove that that is what it is? So think about this. This is a statistics question. I don't know why I'm thinking about this right now. And I don't know why I'm recording it either. If I want to try and find the probability of something happening, sometimes it's easier to find the probability that it wouldn't happen. Okay, so what would have to happen for, instead of saying what's the probability that 2 people share the same birthday in here, let me look at the probability that we don't share birthdays. So I have a birthday, right? It can be one of how many days? 365, right? Now, how many can you have? If we're not going to share a birthday, you have now 364, right? And then 363 and 360. So what happens is that each time you have less and less days you can choose from. Does that make sense? If you find the probability of that, it's easier to calculate than it is to find the probability that we share the same birthday. Anyways, if you do the math, which is beyond the scope of this class, it's about 50-50 for a class of about 23 people. So about half the time I do that, I get 2 people share the same birthday. They're like, oh my God, we have the same birthday. And then it's like, it's not that big of a deal. It's like a coin flip. All right, that was anticlimactic. Whenever it doesn't work, this is exactly what happens. Everyone's like, okay. That's right, but yeah, but what are the odds of that? Even more. Well, nah. That's an interesting question, though. Newton's method. Okay, so I was on the fence about whether or not I should talk about this, but because we ran into a problem last class that we couldn't solve, do you remember I couldn't solve and then I typed it in the computer and I forgot to say solve for y when it was, right? Remember that? And I was like all mad. Okay, so because of that, I thought it would be a great last sort of topic that I could put somewhere on the test. I think once you see it, it's not that bad, okay? Like compared to like optimization, it's not a big deal. So Newton's method. The idea I showed you in class last time. Come on. Well, so here's the idea. If I want to know when a function is 0, right? Trying to figure out when a function is 0. then what this corresponds to are the x-intercepts on the graph, right? Where the function hits the x-axis. Agreed? So let me get to the bottom of this thing. Computer's thinking. There we go. Oh, I thought I had a visual of this. Oh, yeah, there it is. So here's the graph, right? And I want to know where this graph hits the x-axis. So what I do is I pick a single point. Now notice that point is not the x-intercept. The x-intercept looks like it's about 1.4 something, right? Looks like it, about 1.4 something. I picked some random point out here, 3. That's not the x-intercept. What I did then is I went up to the graph, plugged that value in, which gave me the y value, right? Then I found the tangent line there, and then I found where the tangent line intersects the x-axis. That now becomes my second point. That second point that I just got, I now plug into the function again. That gives me a new y value. I bring that down. It hits the x-axis here. And now I have, what, a third point? And I repeat the process. That point I plug into the function. Now let me zoom in. That third point I plug into the function. Look at the slope tangent line where it hits the x-axis. I'm really close to the answer, aren't I? And then I can go again. And I can really zoom in here. Well, I've zoomed in. I think I'm pretty close, right? Go 5. Look at 1.414. This is actually, I'm trying to solve the equation x squared minus 2 equals 0. That's what this program is doing. So the answer is square root of 2. But we know that as a decimal is 1.414. And the further I go, the closer I get to the true value, right? And I can go as far out as I need to. Does that make sense? Yes, that's Newton's method. And that's the way a lot of computer programs work, is they use this, they utilize this method or some variation. So on your calculators, when you type in solve and you put an equation, it's doing some variation of Newton's method. Now, how are we going to use this in this class? We're going to use this formula right here, which I'm going to put on the board. This is the formula for Newton's method. It says, if f of x is a function, and you're trying to solve this, equation right here. If x naught is a starting number, in the problem that I showed you before, what was our starting number? Do you remember what it was? It was 3. Do y'all remember that? Go back out here. Remember I had started out here at 3? We're going to call that x naught, x sub 0. Then according to Newton's method, x sub n plus 1 will be equal to x sub n minus f of x sub n over f prime of x sub n. I'm not going to derive that formula. It's actually not that hard to derive, but I don't have time for it today. So this is what this is saying. You have a bunch of numbers, right? It's like a sequence of numbers. The first one was 3. We did some stuff, and the next one came out right here, didn't it? Our next x value is right here. That would be our x1. So this is x naught. This is x1. The next one would be x3. Then x sub 4. Then x sub 5. And x sub 6. Understand? This formula says that the n plus 1 x is the what? The previous x, right? X sub n is 1 less than n plus 1. Let me write it a different way. Y'all are giving me that look of deer in headlights. Okay, maybe this will work. This is a specific example of Newton's method. If I want to find the fourth point on that line, getting closer and closer to the answer, I look at the third point, the one before it. I subtract from that the function evaluated at the third point divided by the derivative evaluated at the third point. If I do that, that's my fourth point. Then how do I get my fifth point? Do the same thing. So this is like an iteration formula. You start out with your 0 point, then you get your first point. Once you get your first point, you get your second point. Once you get your second point, then you get your third, and then your fourth, and then your fifth, right? And these are marching closer and closer to the true solution. Understand? Okay, so last class, I gave you that problem, and we had this right here. Y cubed minus 3y minus 8 equals 0, right? And we couldn't solve it. And so I went to the computer. And what did we get after we finally surrendered and got the computer to give us the answer? 2.492. Yes? Now we are going to do it using Newton's method. So I'm going to show you how now you actually have a way to solve equations that does not require anything but that. Oh, and I also put here on the notes, there's one little thing here. Newton's method does not always work. Great. Sometimes the x sub n sequence does not converge to the root. So sometimes what happens is that if your function behaves weird enough that that slope of the tangent line doesn't get close, it actually gets further away. And then something will happen, the next tangent line goes further than that, and then it just diverges. Basically, your sequence spreads out. But only functions with certain characteristics will do that. We always try and use this, especially like on polynomials, it should work well. But it's not the magic pill, unfortunately. Where are we? So here's what I'm trying to do now. I'm going to use this formula. There it is. So we are going to now do this equation. We're trying to solve y cubed minus 3y minus 8 equals 0. That was from last class. The first thing I'm going to do is switch it to x's, just so we don't get confused, right? We were having an equation in y, but now let's switch it to x so everything kind of matches up here. Okay? Switch it to x, and forget that problem exists. This is our function. The left side of that equation is our function. So f of x equals x cubed minus 3x minus 8. There's our function. We want to know when the function is 0, right? So we want to know its x-intercepts. To use Newton's method, I'm going to need the derivative, right? Because I'm going to be plugging numbers into the function, which I have there, but I'm also going to be plugging numbers into its derivative. So let's just write its derivative down. Nothing fancy here. Okay? That's it, right? Those are the two pieces we're going to use for Newton's method. Now, let's get our starting point. So I want to know when this thing is 0, right? Let's just try and find where we should start from, right? I mean, what is it? Maybe here's one way we could do it. Let's first just plug 0 into the function. What do we get when we plug 0 into the function? So into this right here, what do we get? -8? Okay. I want it to be 0, don't I? I want 0 to come out. Thank you. What I'm going to do is I'm going to try and find a value that I can plug in that will switch from negative to positive. Then I know the answer is somewhere in between there, right? So let's try 1. What happens when you plug 1 in? Plug 1 right here, you get 1 minus 3, so minus 10. That's no good. Still negative. How about 2? Plug in 2, you should get negative 6. Still hasn't changed, has it? Plug in 3. When you plug in 3, what do you get? 10, positive, right? There, it happened, finally. At 3, it's 10, right? A positive number. And at 2, it was negative 6. That means my answer should be somewhere between 2 and 3, right? So why don't I choose my x naught to be 3? Let's just go for 3, all right? We ready? We're about to employ the Newton's method now. We're going to let x naught, x sub 0, be 3. Okay, x sub 0 is 3. Now, what should happen if this works correctly is that now I'm going to find out what x1 is. I'm going to work it all out. It's going to be a number, right? From that, I will get x2. After I do all that, then I'll get x3. This x0, x1, x2, x3, x4 should be marching closer and closer to the true answer. Understand? So let's figure out what x1 is. Well, according to this, x1 would be what? What x sub 0 minus f of x sub 0 over f prime of x sub 0. So the one right in front of it. So this will be x sub 0 minus f of x sub 0 over f prime of x sub 0. Understand what I did there for the formula? What is x sub 0 though? 3. So this is really just 3 take away f of 3 over f prime of 3. Now I'm just replacing all my x sub 0s with 3, right? 3 here, 3 here, 3 here. So this is 3 take away. Now f of 3. F of 3. So you have to go back to your f function right here. Plug 3 in. 27 take away 9 take away 8. You know what I'm saying here? So what is it? 10? We had already done it here, right? So f of 3 was 10, so 10 on top, over, now plug 3 not into the function, but into the derivative. So come here, plug in 3, what do you get? 9, 3, 27 minus 3, 24. Get your calculators out. This is still equal to 3 minus 10 over 24, right? Well, I'll let you do that. Do 3 minus 10 over 24. You should get approximately, anyone? .5833, right? I stopped 4 decimal places. I think I could, let's go 5 decimal places, 33. That all right? I'm not going to round that because I'm trying to get closer to the answer, right? So I don't want to be rounding. I eventually do have to round though, right? I can't go forever. So let's go 5 decimal places. All right, that's x1, right? That's x1. So x1 is this. Now, what's x2? It'll be x1 minus f of x1 over f prime of x1, x sub 1, which for us is 2.58333 minus f of 2.58333 over the derivative evaluated at 2.58333. See, you're using your calculator to do the multiplication, right? To plug these numbers in, cube it, and do what you need to do. That a computer can do very quickly, right? A computer can do this. You know, you tell a computer, do this. Take that answer, do it again. Take that answer, do it again. And your computer does that very quickly, right? In a blink of firing of a neuron. I mean, it's quick, right? Now, for us by hand, it sucks, but we're just appreciating the method. When you get this, after you work it all out, anyone want to venture their answer? The whole thing. Okay? I'll write down what I got when I did it. I'll show the intermediate. I got, on the top, I got 1.49011. Over the bottom, got 17.02078. And then when I figured that on my calculator, I got, when it was all said and done, 2.49578. Right? That's x sub 2. All right? And we go again. So when do you stop, right? Well, let me do, I'm not going to, well, I didn't do the next one, damn it. Let's do one more, all right? X sub 3 will be x sub 2 minus f of x sub 2 over f prime of x sub 2, which is, I do have my calculator down there, good. Anyone do it yet or no? No? Yeah? $2.49. So this will be 2.49578. That's our x sub 2 minus, when you plug that into the original function, I'm getting 0.05866 over, and then when you plug it into the derivative, I'm getting 15.6868, something like that. Oh no, 675. Which is I got 2.49204. Anyone get something close to that? No? So the question was, when do you stop, right? Is that what you asked, right? When do you stop? Well, how close do you want your answer to be? Within how many decimal places? So remember what decimal places mean, right? When I say, you know, if I write a decimal point 111 forever, this meant 1/10, right? 1/100th, 1/1000th, 1/10,000th, 1/100,000th. How close do you want the true answer to be? If I say just correct to one decimal place, that means I want to be within 1/10 of the correct answer. If I go 2 decimal places, I'm within 1/100th. 3 decimal places, I'm within 1/1000. So the question to me, for me, back to you would be, how close do you want me to be? If you want me to be within 1/1000th of the answer, then what I do is I come here and I say, look here, initially it was 3, right? I'm way off. How do I know I'm way off? Because I don't know the real answer, right? 2.58, I don't know if I'm getting close. Like, I don't know how close that is. You understand? But look, 2.49578 changed, right? It changed from here to here. But look on the next one. Did it change? The first 2 decimal places did not change, did they? And if I do it again, the first 2 and possibly the first 3 won't change. And what happens is the further out you go, you'll notice that you'll get less and less of these changing. So right now, I would feel pretty confident that I'm within 1/100th of the correct answer. But I've only done 3 iterations, right? Your calculator can do these iterations a lot. So your calculator has a built-in tolerance. It says, okay, get the answer, compare this answer to this answer. If they differ by less than 1/1,000,000th or whatever it's programmed in the calculator to be, it says done. That's your answer. So it goes out, I think, 8 decimal places, whatever the computer says to do, and that's when it stops. Now, what was the answer according to the notes last class? It was 2.492. 2.492 is what we used, right? We were happy with that. I think we're there already, aren't we, with our third iteration? That's Newton's method. There's no factoring, right? There's no factoring. There's no weird synthetic division table. The only drawback to it is that if your answer is even like a nice answer, like the answer was like x is 2, you might get like 2.0001 and think that it's not 2. Understand? Closeness, yes, we're talking about closeness again. And that's kind of makes people feel insecure, just kind of close in my personal space. So what do y'all think? Do you think I could give you some unfactorable cubic polynomial and say, find the solution? Use Newton's method? I want you, what? Do what? Yeah, no, it's not going to give you imaginary. That's right. It won't give you the imaginary. Excellent question. It could cross in 3 places. It could, right? Then what you would need to do is have a different starting point. See, I picked a starting point that was close enough to the answer that it worked. If I had multiple x-intercepts, I would need to pick something closer to that one for it to work. Look, take a look at something like this. Okay. Let's say that I pick this as my starting one, right? What's going to happen? I'm going to go up, tangent line is going to bring me back down, and then up and then down, and I'm going to get this one, right? I'm going to get that x-intercept. If I want to try and find the other x-intercepts, because there are, I have to pick a different x-naught and do the process again. So let's say I pick, see, this is where things get dangerous. What if I pick right here as my x-naught? I go up, where does my tangent line take me? To the right here, and then I go where? That takes me to here, and then where does that take me? Way out here, somewhere way up on that function, and where does that take me? It's probably going to wind up taking me back here, right? To this one. So I'm somehow going to miss this one. But if I take my x-naught and instead I put it here, now I'll go out to here, and my tangent line will take me back to here. Oh no, it'll take me where? Yeah, no, here, and then where? Back up, and then where? Back down, and you see what I'm saying? Oh no, this one's going to work here. Here, no, what's happening? I'm getting caught in a loop. So when I said it doesn't always work, that point that you pick, if it starts taking you off to different random places, it's not working, right? So what can your computer do? Well, it can do it once, look at the difference between the two x values. If it notices that they're getting further apart, it knows it's not working. So it picks a different starting point. And it does that. I mean, how many times do you think it could pick a starting point, test that it doesn't work, pick another one? How many times do you think it could do that in 1 second? I mean, it depends on the computer, right? But I mean, you can imagine like hundreds of thousands of times possibly. So the starting point is not that much of an issue for the computer. For us, that would be a huge issue. So on a test, I would tell you what the starting point is. Why? Because I want all your work to be the same. I don't want you to have a starting point of 4 and you have a starting point of 3, and then I have to check each one. Everyone has the same starting point. So all of our calculations should be identical. Mm-hmm. Yep. Which is what the computer would do also. It would go look for sign changes before anything, and then from that it would get an idea of where to choose. Yes, I will give you X naught is. So I will give you this. You will be given a function and a starting point. And so you just what? Have to find the derivative and then apply the formula. And I'll say, you know, correct to 2 decimal places. That means you have to do it until the first 2 decimals stop changing. So like in this one, started out as what? 3, and then from here, 2.58. That changed, right? But from here to here, did it change? Yes. Here to here, the first 2 decimal places did not change. So you'd be done on the 3rd iteration. If I say, I'm not sure I understand. Are you saying what would your answer be? Like, I would just say this is approximately your answer. Yeah. All right. You think you can handle that? Boy, we've eaten up a lot of our class already. You want all Newton's method problems? No, I mean Newton's method. No, the problems don't. It's just that's just to get the method, you know. But I mean, when you look at this now, you can solve a lot of polynomial functions can be solved using this method. But we don't use Newton's method by hand. I mean, it's not made for that. Newton's method is made for a computer. But we want to understand that the computer is not magical. You know, it's not like they programmed a computer or they, you know, created the computer and then one day went, holy shit, it can solve polynomials. Like, wow, this thing's amazing. Like, someone had to think through this and figure out how to utilize the computer to solve the problem. Newton's method is the algorithm for that to work. But it's still calculus, still Newton. Here's the copy of the review. I only brought one per table because I sent this in an email like last, Thursday? So you're at your own table, so you get your own copy. You have it? I have one extra. Oh, wait, I need that one. Hold on. I need that one. I'll give it to you at the end. So, I also posted some of the solutions to this. And in the YouTube, if you go to YouTube, where is it? Go to playlists. Go to past 2014 Cal 1 Fall 2014. So that was last semester. Go down to, where is it? Study group. See that study group video? Okay, so yeah, it's broken up by topic. It's 3 hours. It was a study session that I came in, I think, on a Friday. I invited my Cal 1 class to come to the study group to answer questions on this. I had 3 people show up. 3 people. I stayed for 3 hours. I'm not. No. Because I offer them in the past, and it's only now not because I don't want to, but because you have 3 hours of me going through this review right now. Look, this is part D. Number 1, part D. I'll turn up the volume. So up here, what is it going to be? I have 1 over, not X, but what? So other than the video? That's there too. It's in your files. I sent. Oh. -3 halves. Something called the objective function. I understand. I understand. I understand. Okay, so since I gave this out on Thursday, since I gave this out on Thursday, I am here today to answer specific questions. So, what are specific questions that you have? Yes. For 6A, you do have a specific question? Yes. For the x-intercepts on number 4A, I believe, and if I even did it here, I don't believe I found the x-intercepts. Yeah. Look, if I ask you to sketch a function on the test, all right, the x-intercepts will be solvable. All right? It's going to, if it's a polynomial function, it'll have roots that you can get. I'm not going to give you something you have to have Newtons on. I think this one doesn't have any, right? Right? It doesn't, so you would have to use Newtons. Yeah. Okay, other questions? If you have not seen this review, it is a lot of material. But I was trying to give like repetition of the types of problems. So now that's the review. I'm waiting for questions. While I'm waiting, why don't we take a look? Why don't we take a look at what I actually asked on the test? Don't ask me for a copy of this. I'm not going to give you a copy of this. So let's look at this. 1, find the derivative. I have an arctangent, inside of it a square root. Does that look like any of these here on the review? Thank you. 1b. It does look like 1b. It's an arctan, and then the inside is a square root. The inside is a square root. Kind of looks like 1d, isn't it? I mean, it's a blend of number 1. I mean, it's what is? No, this is the exam. Like this is my. I haven't shown this to anyone yet, except right now. All right, so this was last semester's exam. What I'm trying to get you to see is how, when you look at a review compared to what I asked, like, is the review matching this test? Because that's my biggest complaint, right? For my students, my tests don't match my reviews. That's right. Okay, find the derivative if we have this, x squared times 7 to the, does that look like anything you see here? Let's see, find the derivative. What? Find the derivative? What? 1a. Yes, because on 1a, you have an exponential. I have 5. In fact, the one on here on the review is even harder because it's 5 to the x times sine x. This is just 7 to the 3x. The only kicker is that you have to realize that that's part of a product rule. So I guess that's devastating to some people. I'm sorry, I'm kind of venting here a little bit. I apologize. Just trying to get you to see it's here. It is in here. It's just how well do you make the connections between what's happening. I mean, if you expect a review to be exactly what you're going to see, it's not going to happen. I do. I tell her. She knows how frustrated I am right now with this whole thing. All right. Yes. Yeah, the 8-page, 6-page, whatever. You'll always be able to have that. Yep. Okay, look at this one. 3. Find the derivative of this. Does that look like anything on this? 2D. Yeah, it looks a lot like 2D. Doesn't it? Got some square roots in there. Things. What I just decided to like flip and put the square root on the bottom. I decided to bring the fraction one to the top, and then I threw an x squared instead of an x. But the whole method's the same. Logarithmic differentiation. I have not made the test. This is the actual exam from last semester. Okay, 4. Find the derivative. Does that look like anything on this review? I would say 2b. You've got a function of x raised to a function of x. Logarithmic differentiation, same thing. Yes. Uh-huh. You can always use it. Yep. Mm-hmm. Did I hear? Oh, this was my key that I was grading off of, so I probably just put y there and just looked back up here to make sure. Yeah. Let's see. Find the absolute maximum minimum values of 1 over x plus natural log x. What does this look like? Does this look like anything? It's kind of like 3 what? 3e? Kind of, because it has a natural log in there, right? But it's actually a function that's very similar to 4b, isn't it? Except 4b is a mean value theorem. This one is a closed interval theorem or problem. Both of them require the first derivative. Look at this first derivative. This problem blew this class away. Look at the derivative. The derivative of 1 over x. I don't know how many people wrote that the derivative of 1 over x was like natural log x or something. I mean, like, the derivative of this is this, right? The derivative of this is this. Then what? Set it to 0. Common denominator. Here it is. Set the numerator equal to 0. Put them together. You get a solution of 1. Where is it undefined? At 0, but throw that out. Why? 0 is not in the original domain, right? I'm supposed to be looking in here. Then what? What's this? Plugging in the endpoints and the critical points into the original function and comparing. I didn't even go through the rest of the work. This is closed interval method, right? But the derivative is what killed the class on that test. The derivative of that. I mean, if you can't get the derivative, the rest of it's useless, right? I mean, all right, 6. Another one of these. Find the absolute maximum in closed interval. Oh my gosh, that's almost 3f. That is almost 3f. I took a squared away. Man, I am terrible. I don't know why I am like this. I should not be like this. I mean, product rule, right? Or change it to a quotient first. That's what I did. Then I did what? No, I changed my mind and went back to a product rule. I said, okay, I'm going to do product rule. There's my derivative. Now, what do you do with this? You have to set it to 0. So you look at that, you see e's, you freak out. No, you factor out an e to the x, a negative x. Right? And then you're left with 1 minus x here. Set that equal to 0. And then you set e to the negative x equal to 0. That's the same as 1 over e to the x equals 0. That can never happen. Right? E to any power can never be 0. Look at the graph of v. Right? You see it there? I left it. We've done it a couple of times. I know it's like behind this, back in there. You see e in there still? Right? E is always above the x-axis. So that's no solution. This is your only critical number. And it happens to be an endpoint, so you only have to look at the 2 endpoints. Mean value theorem. For C. I changed a number. I mean, I wish I could pull these tests out and show them to you and be like, look at this. Then they go and, you know, complain that I should shut up, shouldn't I? I am recording this. I mean, how frustrating is it? I mean, can you understand my frustration? I think this is more than fair. If I had been given a review as a student in Cal 1 where the question was off by a degree on the polynomial, and that's what I'm being asked, after being told you might be asked a question like this, that would have been a gift. You know? Well, no, don't thank me. Don't thank me. I'm just trying to. If anyone does not like the results of this, everything that's happened in this class at the end of the semester, if you don't like it, that's fine. And constructive criticism, I am happy to take. But do not go onto some random website and say that my reviews and my tests are completely different, because they're not. They're not different. I mean, it's okay. Next one. Find the local maximum. Man, I've done this in class already for sure. Wait, max and min, increase, decreasing, is that on here? 5C, oh yeah. Okay, so here's what got everyone on this one. On the review, it was already multiplied through. So look, the first step was to multiply this here and this here. What happens when you do x to the 2/3 times x? You add the exponents, and so you get x to the 5/3, and then you do x to 2/3 times 5, you get this. Again, mushroom cloud. What's weird about that is in the homework, right? This is the way the book does it, right? The book does this version. On the sketching problems, which I know you've all done already, but probably don't remember it, right? Sketching, this 4, 4, 4, I'm referencing or perhaps, maybe it's, maybe not. Maybe I did pull that one out of the air too much. Okay, I'll give you that. I'm sure I did it in the notes. I think in this class, I didn't do one like this. Because I've toned down the sketching problems for this class. Like, we never sketched anything like this, did we? No. Right? I kept it pretty much polynomials, pretty clean. Yeah. So that's what I would expect on the test. But if it's on the review, you know, it should be fair game, I would think. Okay, what's the next thing I asked? Sketch this. Cubic polynomial. It's very much like 6a. Even better, though, because when you take the derivative, it's quadratic. And you can always solve a quadratic for 0. So 10. A farmer builds 3 identical enclosures along a riverbank as shown. See, I'm even like, I'm not even being sexist up here. I'm sharing the burden of this, you know. I'm kidding. This farmer, does not need to put fence along the river. So here's the river, here's the fence. Total area of the 3 enclosures, 800 square feet. This is very much like the problem we just did, okay? The only thing is that you have to put fence here, 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 and here, but you do not need fence up against the river. If they want to go and jump in, they can, but they're afraid of water, apparently. So find the dimensions which will minimize the amount of fence required. Same exact problem as the one you just did in the quiz. There it is. Ah, some limits. See if this looks like anything off this review. Well, I gave them this, yes. It's kind of like B? Yeah. Oh, yeah, it's switched. So the derivative of the top, right, well, first plug in 0. What do you get when you plug in 0? 0 on top and then 0 on bottom. So do L'Hopital, 0 over 0, derivative top and bottom separately. Derivative top here is e to the x, derivative bottom, 2. So let x go to 0. You get 1 over 2, 1/2. This one was bad, real bad. Yes. Well, does this look like anything off of this review? Well, what did I do here? Cosecant x minus cotangent x. Rewrote it as a fraction, right? Do you think that that's a lot to ask to rewrite this as a fraction? Get a common denominator? Let x go to 0, you get 0 over 0, and apply L'Hopital's rule once. If you look at h on here, it's basically the same idea. You had 1 over sine x minus 1 over x, and you put them together with a common denominator, and they did the same thing. You get it that way. So when your answer, are you trying to take a picture? I'm just going to, go ahead, I don't mind. Well, you stop when you do the limit and you don't get 0 over 0 anymore. So like here, when I plug in 0, cosine of 0 is 1. 1 minus 1 is 0. But sine of 0 is 0. So you get 0 over 0. Do L'Hopital. So derivative of top is sine x. Derivative bottom is cosine. Now plug in 0. Sine of 0 is 0. Cosine 0 is 1. 0 over 1 is okay. That's 0. Yeah. Mm-hmm. Whichever way you like. Like, do you prefer the graphs over the unit circle? I mean, that really, I think, is dependent upon you as student to student. Yes. Oh, yeah. You should get the same thing. Yeah. Yeah. You know, when I do both. I like all. It just depends on how I feel when I'm looking at the problem. Like, does this seem more suited for the unit circle? Do I need to look at the graph? Yeah. 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 Either way, you should get the same result. The only thing I would say is on the unit circle, like let's say you're approaching pi over 2 from the left. Then on your unit circle, you're approaching from this side, coming in like that. No, see, that's what I'm saying. Like, if you're approaching pi over 2 from the left, on the number line, pi over 2 from the left means you're smaller than pi over 2. So on the unit circle, that angle, this is 0, pi over 2 is up here, would mean coming in from this side. So you just have to be careful with that rotation. The rotation is counterclockwise, so. Don't you have one? Isn't there one on there in the formula sheet? I thought I've seen. There's a circle. I see a circle. No, you can't use the unit circle. No. You need to know the unit circle. The graphs are on there, so that's always your fallback on that. Okay, let's keep going here. Another limit. This look like anything here? Eight I. What I'm doing here for this limit is I'm trying to get this x squared out of here, so I call the limit y and I do natural log. This is very similar, but not the same as this problem. This is an equation, y equals this, right? Find the derivative. You're finding the derivative of a function, as opposed to the one we just looked at, which was you're trying to evaluate a limit, right? Trying to find a limit. This is going to 0 to the 0, which is a bad situation. So we employ the natural log to be able to drop the power out, but it's not the same type of problem. The reason why I'm saying this is because what I've seen in the past is students not distinguishing between those two types of problems. And so they try and do the limit stuff on the other one. They try and do this one as a derivative, and it's not the same. You go through and you find everything at, you go through, you pull your power out, go through all this, you get infinity over infinity. Well, should I talk through this or not? Okay. This one's, right now when you plug in 0, you get 0 to the 0, which is not good. Remember all the indeterminate forms I put up here? Okay. So whenever we have 0 to 0, we try and get the power out. You can't just drop it out front, so you need a natural log. So we call this thing y so that we have an equation, and then we take natural log on both sides. The natural log passes through the limit and is now sitting next to this big ugly thing. The x squared drops out in front. Now I have a product, right, instead of a power. Let x go to 0. 0 squared is 0. Natural log of 0, the graph of natural log, goes to negative infinity. So you basically have 0 times infinity. I did not put negative infinity because, again, this was my key. No one else was looking at this. I realized, like, that's going to negative infinity. Doesn't matter. It's an indeterminate form. So now, anytime we see 0 times infinity, you drop one of them down to the bottom. So I chose to take the x squared and drop it to the bottom as a 1 over x squared. And then this right here, as a reminder, is this, right? Because I'm getting, when I do this, I'm getting infinity over infinity. Now I do L'Hopital. Derivative of the top is 1 over x. Derivative of the bottom is this, which is the derivative of that, right? Negative 2 comes out, x to negative 3. Then I flip it, because I have a fraction over fraction. I flip it, and when I do that, things cancel, and you're just left with, you can't tell here, but you're just left with x squared on top and negative 2 on bottom. You're left with x squared over negative 2. And now when you let x go to 0, this is just 0. So you get natural log of y, which is the left side, which came down the whole time with me, is equal to 0. But you're trying to solve for y, so you bring in e on both sides. E to the natural log of y is y. E to the 0 is 1. So the answer, all of that work, was just 1. So I'm thinking that, you know, on this review, 8, I, and K would have both would have been good practice problems for that one. What's that? I don't even know what that is. That's the end. No Newton's method on theirs. So you'll have a Newton's method. I don't know. I mean, this can be somewhat involved. You know, this is a long test. I mean, just look, you just did that in class, right? I gave you 20, I think I gave you 20 or 25 minutes to do that. That's what, just one problem out of 13. So, I mean, I have to be careful with the length. Maybe my tests are too long. Maybe that's what they should be saying. His tests are too long. That I could swallow. All right, so what else? I mean, it's ready. Class is almost over. Wow. So our test is on Thursday, right? Thursday, right? Well, I'm willing to have it on Tuesday if you're willing to have new material on Thursday. But I don't know. I don't want to change things now. You know, I've already committed. You'll be responsible for it. You have to be responsible for it. I mean, let's just take a vote. I just want to see. Remember, this is a democratic totalitarian. You know, you can vote, and then I just sit there and go, nah, it's my decision, right? Let's see. So how many of you, let's stick with Thursday. This will be a good time for the clickers. How many of you just stick with Thursday? Okay. That's about half. Okay. How many of you, let's move it to Tuesday? Okay. So we don't have a majority. We don't have a strong majority. So we're just going to stick with what we have. What's what? Yeah, antiderivatives. No, that's the beginning. There's overlap here. We're supposed to get into U substitution with integration. So we're supposed to be, well, I mean, we're supposed to go a little further, so. Thursday it is. Did I post this? I did. Not this one. The review one, right? This I did post the hard copy of. I did not do every problem in the review session. The 3 hours, not every problem was done. So if there's anything that was not done on here that you'd like to see or need to know, the answer, just get with me about that. All right, but don't get with me an hour before the test on Thursday. Get with me within the next 24 to 36 hours. All right, you can do it. I feel good for you. Good question.